Okay, as promised, I'm going to go through the rest of these hints for this exam, which will rework. If you don't have the document, it is posted out in an email to you all. And I did first in class, I went through around question 31. I'll go back and do those for those of you who had to run away for car problems or weren't in class for swine flu or any other malady. And so we'll start with number 30. And I'll give you just basically the quick hints here. And a little bit more insight so you can kind of try to pull out that this stuff is not about just getting an exam. It's something that you're going to recognize later when you're doing reading. Okay, so number 30 is what's the Reynolds number for water flowing through a 24-inch diameter pipe at velocity of 5 feet per second? First, let's remember that Reynolds number is the ratio of the inertial forces to the viscous forces. So the fact that something wants to keep going is captured in its diameter times its velocity. The fact that something is pulling back behind it or pulling it back is captured in kinematic viscosity. The key here is that you're dealing with a number, therefore the units have to be the same. You need to put the diameter, and since you generally know that the kinematic viscosity of water is 1 times 10 to the minus fifth feet squared per second, and because you should always be working, sorry about the glare, we'll work on that next time, but because you always should be working in feet, pounds, seconds, slug units, then you need to convert that 24 inches to feet. Okay, 31, it's a question of converting gallons to cubic feet and minutes to seconds and knowing that Q is volume over time. And you get that from the definition, cubic feet per second. Number 32, one more time, you drop a ball, it moves h distance, falls h distance, it converts its potential energy to kinetic energy. mgh equals 1/2 mv squared. Sooner or later you'll get how often you cancel out mass and you get the square root of 2gh. 33. This problem was given, or the problem now, which is going to be described here, has 150 feet ahead. So the most velocity you're going to get out of this system is the square root of 2gh. What you have is given to you is a pipe size and a pipe material type. The pipe material type gets you what we see in the literature as epsilon, which is the roughness, right? But you're interested in the relative roughness, which is epsilon divided by diameter. That will get you to a good guess on the Moody diagram, because you remember the Moody diagram will look something like this, where this is the friction factor F. See if I can move this. This is the friction factor F. You've got something that's for a long time very stable here, because this is a particular curve, which is relative roughness, and here is your Reynolds number. And so if you know your relative roughness, you can very much quickly guess at your friction factor. So that's the start of that. You have to remember that 6 inches is 1/2 foot, and so your roughness for a cast iron pipe divided by 0.5 gets you your relative roughness. That gets you a friction factor, and then you can go to a calculator and do Bernoulli's equation with the inputs of what is the length in feet, what is the head available, what is the friction factor, what is the diameter of the pipe, and it should solve for you a flow rate. Now, it will come out with a Reynolds number, N sub r, and you should check that again in your Moody diagram to make sure that that Reynolds number is in the flat section of the pipe, because this is an iterative process. Though in all reality, if you're in a pretty fast-moving system, you should be able to guess the first time at the friction factor. All right, so you'll see what you know is that it drops from 1400 to 1250, so it dropped 150 feet ahead. Therefore, you know, in fact, it won't be any faster when you talk at velocity than the problem before that, which is, well, how fast will a ball that's dropped 150 feet, how fast will it be moving in feet per second? So that was number 33. Number 34, you have to kind of draft out in your head or in your calculator and realize that for all intents and purposes, it's starting with 1,400 feet of head or foot-pounds of energy per pound of material, and it goes down to 1 velocity head above the elevation of the exit. And then at some other point here at station 1320, right, which I actually, when I'm putting out this exam, I will notice that I'll have to go back and send an email out because I didn't have the pencil in what I had. So you have to look at the elevation at 1320, measure up to the hydraulic grade line, which is one velocity head less than the energy grade line, and that distance here is your feet of pressure head. And so you know that P over gamma is the pressure head, and so you can solve for the pressure, and it will be in units of pounds per square foot in this case. If in fact you close the system down here, the energy grade line is flat, and you're essentially looking at Pascal's equation, where in fact the pressure head will be equal to the elevation of the surface of the water minus the elevation of at 1320. So I do not have that here. I'm looking at the timer here trying to get this done in 10 minutes. I will send an email out on the parts of this exam that were not penciled in, I think, if I can find it. Otherwise, I'll just make one up. All right, that was 35. So that was a static system. That was Pascal's law, which is essentially when water's not moving, what Bernoulli's equation becomes, which is the change in pressure is equal to a minus change in elevation times the unit weight of the fluid through which you're quote-unquote traveling through. All right, 36. Now you have to go back to the general aspect of using the computer program and realizing, or the calculator program, that when something is flowing a lot less, it's going to have a less slope, and so you're going to have, right, you're going to have the energy grade line that's not going to be falling as fast as it is when it was running very quickly. So you have to go back to Moody's diagram, base it on an initial flow rate and a velocity, get a new friction factor, and calculate it out. Since you know the velocity for the reason that you knew the flow from the problem 2 previous. You know the area of the pipe. That gets you the velocity. If you know the velocity, you can plug it into this equation here because you know the Reynolds number, you get a friction factor, and then you can calculate using the Bernoulli's equation. And the Bernoulli's equation for us, at least in the short term, is going to be plugging it into that calculator when you're given the inputs of friction factor, head, length of pipe, diameter of pipe, and see what you get for output. All right, so 37 is again converting everything to pounds per square foot and a Pascal's law problem, where in fact you have some pressure up here, right, and it's in the order of 60 psi, which converts up to about 130 feet of water, and then this other pipe is down below it, so you add up those two pressures. You add the, more or less the pressure head from the pipe, which from the pressure tank, which is in psi. You need to convert it to pounds per square foot. You see the theme here: feet, pound, seconds. And then you're down 100 feet in elevation. When the water's not running, that's what you feel. When it starts to run, it loses a lot of energy and it's transmitting as it's traveling through, losing it to friction. And so that's why you won't necessarily feel all of that when the water is running through the pipe. Number 38 goes back to Bernoulli's equation, guessing at a velocity, calculating a Reynolds number, getting a friction factor, plugging it in the calculator, getting a new Reynolds number, a new velocity, going back to the Bernoulli's chart, doing that a couple of times and 3 times until you stabilize and get a stable equation. So if you remember, you guess at a velocity, you know that the Reynolds number is dV over the kinematic viscosity, being 1 times 10 to the minus 5th feet squared per second. You then put that in, get a Reynolds number, get a friction factor, take the friction factor, use Bernoulli's equation, get a new Reynolds number, get a new friction factor, and you iterate through the solution. 3 times around and you should have it right. Number 39, figure it out. How many feet is it along the river down to New Orleans? Right in the news yesterday as they found the Corps of Engineers and the U.S. government liable for not maintaining a waterway there, and that being part of the cause of Katrina. So they didn't talk to me, but the fact that I've talked about it, you know, maybe every day, it means I'm going to hit sooner or later. All right, so that was the story there. It's the change in height over the